Hey everybody, it's been a while. And because it's been a while, I feel like I've got to do some review. So today we're going to try to go back over and tie together the different parts of electric potential, also known as voltage, and electric potential energy. And I think once we get a complete picture, you guys will feel better about what we've done. All right, I hope you guys did okay on the SATs. I'm going to limit my other comments to sort of live action. Yeah, there's no need to say that. I should edit that out. So here's what I was thinking today. What we would do, I kind of already laid out some notes that we'll draw some pictures on. And we'll go through, and I think we'll end it with a problem today. But first, take out a nice clean sheet of paper, put a title up on it. It says Potential and Potential Energy Review Notes. This idea of accelerating potential. And EV, who knows what EV stands for? Yeah, that's right, the electron volt. It's a unit of energy. Good. Now, just to remind you, if you look at this picture of a positive charge, what we are looking at is the electric field produced by a charge, and it's related to KQ over R squared. That clearly shows to me that the electric field is an inverse square relationship. Now, if I place a positive test charge, now this positive test charge, we always say it that way, and it's basically we are ignoring the effect that it has on the field at that point. So the question is, which way would it experience a force? Of course. That rhymes. And we could find that force by saying QE. Now that's easy with one test charge. Heck, it's easy with two test charges. We got to be, with two charges. We got to be careful when we're adding the electric field at any point though, because it is a vector. So we have to take into consideration the direction as well. Now, the other type of problem associated with electric fields is where we have a uniform electric field. Go ahead, just draw it. A whole series of lines. Good. So that uniform electric field would cause a charge to experience a force. So if I place a positive charge in this field, it will experience a force in the direction of the field lines. If I have a negative charge placed in that field, it will experience a force opposite. Of course you know that. Good. Bask in the fact that you already know this stuff. Let me ask you this though, since I could feel your overconfidence through the screen right now. If I had a charge that was already moving, let's pretend I had a positive charge moving upwards through this with a velocity V. Velocity V, not voltage. What would the path of that charge look like? You know, show me with your hands. Yeah, it's going to go whoop, whoop. It's going to be parabolic, right? Because the key is that the force is perpendicular to the velocity at first. And that force is going to continue to cause it. Wait a minute. That's kind of like if you take your computer or phone right now and flip it on its side. That looks like a gravitational field, doesn't it? With a mass moving across it and gravity pulling it down. Good. All right. I'm going to delete the last part of that picture because that'll just confuse you some later date. But F equals QE. And the sum of those forces would cause the mass to accelerate. Next, when I have a charge like this, we spend time using that PhET simulation to try to show lines of equipotential although many might pronounce it equipotential. Depends what part of the country you're from or how good you talk. But basically, I think you guys saw this really well when you did that assignment. I was impressed by your work. If we make the amount of the change in voltage the same, what we should end up with are these really nicely spaced circles around a point charge. Now, they're not going to be evenly spaced because the potential V around any point charge is going to be KQ over R. So potential is related to 1 over R. So I'm a little disappointed in my circles here. Just maybe I will be able to edit this later and fix it. Oh yeah, that looks good. Doesn't this make it so you can sleep at night now? Whew, it does for me. Now, the beautiful thing about finding the potential at a certain point away from a charge, let's just call that point P, is that it's a scalar. And as a scalar, all we have to do is add them up. So the sum of the volts at P would just literally be the potentials all added together from different charges, right? That's it. The key when you add them together, though, is that you've got to include the signs. Okay, again, all review. Next, though, actually, this is still review. Let's say we take that positive charge and we plop it at the origin in a graph of potential versus distance. And you know what? I'm going to use R. I've seen this done on the AP test and sometimes in textbooks. Instead of using D for distance, sometimes we use R. We do that with gravity. Now, because the potential, V, is KQ over R, and therefore proportional to 1 over R for a given charge, our graph would look something like this. Now, if this point had no volume, it would be a perfect asymptote and it would never stop and go all the way up. But we can't have anything with no volume. So at some point, it's going to reach that maximum as we get closer and closer. Okay? Now, we could look at it if it was a negative charge. What we would see is that will go down. All right. Not so bad. What if I have 2 plates? Now we're getting into something a little bit new. And if I were to hook up a battery to those 2 plates, so I'm going to put the positive terminal. Now, this is from last year. I just hooked up the positive terminal, which is the longer side, and the negative terminal, which is the shorter side, to 2 sides of a capacitor plate, or just, how about 2 plates? They're separated by air. So because they're separated by air, charges can't go from one to the other. So when I first connect this up, what will happen is that positive charges will start to collect on the top plate. They will create a field that extends across space. These are field lines, not moving charges. They'll do that until the positive charges on the other side. Oh, Ben Franklin. He did so many great things, but on this one, he really screwed up. You know that I know that you know that it's not positive charges that move. We all know it's negative charges, but Ben didn't know that. So we talk about the flow of current as the flow of positive charges. It's unfortunate, but it is what it is. Now, those field lines would cause the electrons to collect on the other plate and create a uniform electric field. Now, come back. Are you ready? Because there's another formula that we would utilize when looking at the electric field and the potential difference between these two plates, and that is that the electric field would be the potential divided by the distance. Or, as I often say, the voltage is equal to Ed. Unfortunately, we don't have any students named Ed in class. That'd be helpful. Ed Kukowski. He graduated in 2002. That was a while ago now, though. Now, those field lines are going to point from the positive charge to the negative charge. And if I place a positive test charge there, it will experience a force. And that force will cause it to accelerate. But you know what else is right here when the charge is not actually present? Do you know what we have at that spot? Yeah, you do. Yeah, you do. It's the same thing that's right at this spot, right here. Whoop. See it? Right here for gravity, it's voltage. For the plates, it's voltage. It's potential. So we're going to be able to look at the potential at that point. Now go back to the PhET simulation. Pay attention. Here it comes. Ready? The lines of equipotential, by definition, are perpendicular to the field lines. So if I were to draw in a line of equipotential here, it would cut right through the middle of that. And everywhere on that line, the potential would be the same. Then, just like our PhET simulation, if I wanted to show this nicely to scale, I would make sure that the separation between each line would be equal. Let me try again with it. One more picture. I think I can fit it in right here. So if I have two charged plates, and one plate is at 50 volts, and the other is at 0 volts. Why is that the voltage? Because it's hooked up to a 50 volt power supply. That is going to create field lines that point from the positive plate to the negative plate. Do you guys mind? You ready? I'm going to change that. Relax. Hey, stop moaning. That's why you have an eraser. Let's make it 40 volts. Just makes it easier for me. Okay. Now, if I were to draw in my lines of equipotential right down the middle, that potential would be 20 volts. If I bisect that on each side, I'd have 30 and 10, and each division would be equal to 10 volts. So that a charge, as it travels from the positive plate, a positive charge that is, and travels down, the potential is going to decrease. What is that potential energy turning into? Yeah, that's right. It's turning into the kinetic energy. Good. Okay. So